Good evening. Good evening, doctor. You have to unmute if you are muted. My Dr. Gatema, good evening. Abayomi, good evening.
Hello, sir.
Good evening. Well
Good
done.
evening, sir.
Good evening. Hello.
Good evening, sir.
Good evening, Samira. I first of all, I didn't know that it was 10 I put before. So I have to redo it to now send it. Maybe people are confused. Because
Yes.
when I started, because by 8 when I started, I didn't see much, only two people. And I felt maybe because it was a mistake. I didn't know that it was 22, 10. Supposed to be 10, 8 to 11. Actually, though it's 8 to 2, but actually give space so that if you pass, the thing will not stop. So it was not mistakenly put 22, which is 10. So when I started now by 8, only 2 people, and I only do it. I redid it. And actually, maybe people, and I've sent it to the link. But many people now are not looking at it again. I've sent it to the link. All those links.
Yes, sir. I'm going to send message to the group.
And I said I send new link. They should use that new link. New link is 8. The old one is starting by 10. If you know, use the new link I sent. Maybe I have to delete that. Mm-hmm. So we have a lot of people now, and that's great. Welcome, everyone. You know that you have to unmute if you want to talk. So this is 20 minutes past. Wait too. Okay, good evening, everyone. Today we'll be talking about assumptions around hypothesis test. We started with issue of basic concept where we know that statistics is very descriptive and inferential. And the descriptive, we say that probability is the bridge. It's related also. It's the one that binds them together. And we started our discussion with descriptive statistics. We talk about probability. We just all started with basic concept, descriptive statistic, probability, and yesterday, introduction to inferential statistics. So before we start running those inferential tests, these hypothesis tests, going the inferential statistics, I already said that we are looking at two methods of inferential statistics, which are hypothesis testing and confidence interval, which we had introduction to yesterday. Now, before we start a particular test, and even the confidence interval, and we hand on with that for us to look at what are those assumptions, what makes you to choose a type of test. Before you can just say, okay, chi-square. So what makes somebody to choose chi-square? What makes somebody to choose t-test, ANOVA, regression, linear regression, logistic regression, all sorts of different tests. What makes person? So there are some assumptions around it, and that's what we are going to. And part of the assumption related to what we did yesterday concerning, and therefore concerning probability, and even yesterday, where we're talking about skew distribution in the practical session. So now, these are massing. One is virtually all hypothesis tests are actually the same thing, dressed up in different names. It's the same logic. Whether chi-square, t-test, ANOVA, all of them, it's the same logic. It's just like either you say you are a doctor, you are a nurse, you are a lawyer, you are anything, you are all human being. So it's just that you just dress yourself, oh, this is according to my profession. But you are all human being. If somebody is sick, is sick. So you need food. The basic necessities of life, everybody needs this. So the hypothesis tests are actually the same thing. You will go to see. So look at what Strainer, and Norman said. Nearly all statistic tests are based on signal to noise ratio, where the signal is the important relationship and the noise is a measure of individual variation. It's like the signal that, oh, you are looking for association between two variables. Oh, the numerator is the signal. Oh, is there an association? So the noise that we will say there's no association. Denominator. Numerator is the association, the signal, while the noise is the denominator. So it is when the signal is far more higher than the noise that we see, we can hear very well. So there's no, just like if you are tuning your radio, you will get background noise, either you like it or not. But until you tune, until when the signal is far higher than the noise, and overshadow, you can hear very well. If the signal and the noise are the same, you won't hear very well. So, and if the signal is 1 and is a value and the noise is a value, it's the same value, it will give you 1. If the value of this noise is higher than the signal, it will give you 0 point something. You know, if you divide, if the numerator is higher than the denominator, it will give you 0 point something. Then for you to say there is real signal, there is association, the signal must be far higher than the noise. In such a way that when you divide, it should be greater than 1, meaning that the numerator, which is the signal, is far more than not far more than, it must be above 1 very well until it reaches a critical value where you just say, this one is not due to chance, so it's a real signal. So that's just a layman way of saying it so that you can know what you are preparing your mind for. So general formula for a test statistic, general formula. Variability between groups, which is the signal I said. At least, is the difference between the different variability here means different. The difference we are looking for between the groups, the two groups, is the numerator. And the variability within the population is the noise. Can you see now? Let me give an example. If you say that, okay, blood sugar of female and male, we are comparing, and the mean blood sugar of female is 65. The mean for the male is 60. You can see observe difference of 5 in the mean blood sugar for the two. So will you just say blankly, these women, they have more blood sugar than male. Look at the average. But you have forgotten that is the average for the female that is 65. That's for female that far below. In fact, far below some male that have blood sugar on their own, far below some male. And also, there are some male that you think, oh, their group has lower blood sugar. They have blood sugar far above the mean for the female and above some female. So the issue there is that we are usually, this average we have gotten now, for us is the signal. For us to see, is it really good average? Is it really different? The difference we are seeing in the blood sugar. I'm just using as an example. So you have to now look at the variability in blood sugar among individuals. Forget about male or female. If you mix everything together, what are the difference? How does it vary? If the variation is even much more, far more, where you can even see some male we have far more than some female. So female have far less than some male. So variability is so much. That 5 difference you are seeing may not be significant. So may not mean anything. It's a bit by chance. And the way we can do it, the only way to know it is to put that 5 variability as numerator. And then put that EN, the variability within that population as denominator. So there's a way you calculate the 2 variability in a different way. So when the variability, you can say that the difference is significant when you see that the variability within population is far less than the variability between the 2 groups. In that situation, and when you divide it, it will be greater than 1. Not only greater than 1, it will be far greater than 1 until it reaches a critical value where we are going to see that critical value. It is something like the degree of freedom we talk about that will let you know what is the critical value, because it has something to do with the sample size. The critical value, the test you are doing, and so the degree of freedom has something to do with that sample size. Now, it's the same thing. You see, test statistic, observed minus hypothesized value over standard error of observed value. You see this thing. Because the real issue, what do you mean by observed value? Observed value is the value you have got it when you summarize. You say, oh, women, the average is 65. Men, 60. The observed difference is 5. That observed value is the observed difference, because the difference you are using as denominator. You want to remove hypothesized difference. Hypothesized difference is the difference when no hypothesis is true. When there's no difference, what will it be when there's no difference between the blood sugar of male and female? What will be different be? So who can answer that question? I want to prick you so that you are aware. It's a workshop. Somebody can unmute and say, what will be different be if the observed different and the hypothesized different? What would be hypothesized different be? Because the hypothesized different is the mean, is the same thing as the difference, the value when no hypothesis is true. And no hypothesis says there's no difference between the two. What should be the hypothesized value? Nobody? So observed difference, which is 5 here for that example again, will minus hypothesized difference over the standard error of observed value. So the variability within, what measure is the standard error? You remember, there's something I just remember I didn't tell you. When we're doing the introduction to inferential statistics, when we talk about standard error, and all the sampling distribution, standard error. So we didn't actually, there's something I need to tell you. You know, we said that the standard error is standard deviation over square root of sample size. If you increase the sample size, it will reduce the error. If you decrease the sample size, it will increase the error. Now, what is the usefulness of this standard error? If standard error is small, it means 2 things. It may mean 2 things. If the standard error is small, it may mean that the attribute you are studying does not vary much in the population. For example, we know that height does not vary much like weight in the population. So another thing is that if it is small, it may mean that the estimate you have made for your sample is very close to the population parameter. Can you see? When the standard error, it's a measure of variability here now, because it says population standard deviation. We say the standard error is a standard deviation of sampling distribution, which is believed to be equal to the standard deviation of the population. That standard deviation of the population just measure variability. So if it's very small, it may mean that the attribute is not very much. It may also mean that the estimate you have made is very near, very close to the real parameter, even though you don't know the real parameter. But if the standard error is very large, it may mean that the attribute is very wide apart, like in a situation you say, the weight very much. There are other things that vary even much more than height in the population. Income very much, especially in developing countries. In European countries, income do not vary much among people. You see, there's close margin. Some people cannot reach more than 38 years. Some people may not even have anything. If you have, some people may not even earn adult, maybe working, may not even cannot gather 10,000 in a month. Wow, some people are making 5 million. So the variability for income in Africa is very wide. So the standard error will be very large. But in a place where the variability is very small, the standard error will be small. It may also mean if the variability, the standard error is large, it may mean that the estimate you have made in the sample is far from the real population parameter. Can you see now? So is that standard error is the one that is acting as noise. That is, if you see a difference between two groups now, and you now see, the standard error is even large. By the time you calculate it, it may even give 0 point something. In fact, that is, even the standard error may be far larger than the difference you have seen. Because the thing varies. So if the difference even vary in population, why do you not say ordinary 10 or 2 or 5 is significant until you put it to test? But if the standard error is very small, and it may mean that, as I've said it, the attribute, is very, it does not vary much. In that situation, the standard error, the denominator will be small. The difference you are looking at, numerator will be larger. And when you divide it to be greater than 1, it will be far greater than 1. It has reached a critical value and is significant. So another way of saying it is, the statistic is variance explained by the model, systematic variance over variance not explained by the model, not systematic variance. When you say model, it just means your research. Your research, your alternative approach to say, you are looking at difference between two groups. That is your model. But that one inherent the standard error, which is inherent variability, has nothing to do with your study. So it is when the standard, the variance explained by your model, your study is far higher than the one that is intrinsic, which is the one within the population, which is the standard design. This is far and it's greater than 1. Not only greater than 1, it's far greater than 1. But with the help of something like degree of freedom, we get to know. Now, we want a t-test is an example that is easy to conceptualize. That's why when I want to introduce what I call it, this hypothesis test, I use t-test. It's simple. For example, now this is pair t-test. This pair t-test now, we will still do it. What it means that you look for the difference, mean of the difference. In pair t-test, you may, for example, now you may measure people's blood pressure sitting. The same people, maybe 30 people, you measure the blood pressure for each of them, you record it, and now say stand, you measure it. You get different reading. You now, for each of the 30 people, you now minus 1 from the other. You may decide to minus the one you think is smaller, generally, from the other one. But even if the other way, you still get the same thing. But to remove too much negativity from your working, you may decide the one, because even the one you think is smaller, it's not all of them that will be smaller than the other one. So, but where you know that it's higher, you now remove the smaller one from it. You now calculate the mean of that difference, T, mean of the difference. Then, if you remember, this is T, mean of the difference now, is the one that look at the variability between the sitting and standing blood pressure. You remember that that is the but the which is standard error is this standard deviation of D over N. S is standard deviation of D over 12 of sample size. This is what? Standard error. So we have said standard error is standard deviation over 12 of sample size. So can you see the formula for pair t-test? D over standard error over 12 of sample size. That is the T. That's the formula for T. Can you see? It's very simple. It's very simple for PAT. The one, if you look at it now, this body, look at the variance you are looking at between your study. While the standard deviation SG over square root of sample size is your inherent variability, which is the error. Let's look at example of another one. This one now, the one we just discussed is pair sample set treated. But this one, independent sample treated, you have two groups. When you took your blood pressure, instead of the same people sitting and standing, you just say maybe either sitting or standing anyway. You have two groups of people. You may say male and female. Let's do their blood pressures. They are separate. They are two. So a mean for one will be X by X1. Mean from 2 is by S2. Can you see now? So the difference you're looking at is the by X1 minus by S2. Now, I ask you a question. Nobody answer. When I say that that is, this one is the observed value, is of that observed different. The hypothesized different is, that is, if both of them, that one's in the population, that's why you are seeing mu1 minus mu2. So if that is the different in the population, when no hypothesis to, when there's no different. Now, all over say square root of standard error. That standard, it look a little bit difficult because it's talking about two samples. The other one is one sample. That was just a standard error of D over square root of sample. Then this one that are two samples is just a rigorous way of it's just some mathematics just to say, okay, S1 square over N1 plus S1 2 square over N2. This is formula for some independent sample titers. Can you see? Now you will see the question you did not answer. If no hypothesis is true, then hypothesized difference will be 0 now, because it means that both of them are the same. If something is 50, you remove 50 from it. Both of them, it gives you 0. So it's out. That is why in the formula for the t-test, independent sample t-test, you won't see that one there, because that one is always 0. That's why you see. You remember this is the formula. We are not teaching formula just for you to know the logic. Once you know the logic, you know how to use the computer to run. You are fine and good. Then the third example is one sample t-test. It's close, almost the same thing with the pair sample t-test. This one now is one group. It was, for example, now if you do the mean blood pressure of people, maybe 30 people, you measure their blood pressure of students in MPH or in non-university, and you just selected some to measure their blood pressure. It's just one sample. And then from the literature, what has been published, they say, the blood pressure of average blood pressure or systolic blood pressure of 9 university students is this. That one is the population value, means 0. So you want to see, okay, now this one I've collected now, is it different from the population value? Because when you collect one sample, you have to now do their mean, you get by X. But that means 0 is the one they give you. So this was one sample t-test. It's only one sample. You are comparing your finding with one value, but you don't have access to their own data. It has been published. It's just a value. So that is what called one sample t-test. So the same thing, now say T is got bar 1 minus bar 0. Bar 0 is 0. Because the issue there is that, it's not 0. It's the value, because the value they give you, means 0 rather, the value they give you in the population, it is believed that it's population value. So you now want to, that is hypothesized value. That is the population value. That's hypothesized value. So you want to see, is it different from this by heck, which is this one you got from your study. So by X minus all over square root of, can you see, all over standard error, which is standard deviation all over square root of sample size. Can you see? So you see t-test now is just explains the simplest way to allow you to conceptualize, even though it's not the t-test we want to first do. Sometimes I do it first, but later I discover that even the t-test is easier, far easier than chi-square. But because many people, they have heard of chi-square many times, even though they don't know much about it. But if you talk about you hear chi-square. And that is why, because one day I was doing workshop, and I decided to, after I started with t-test. Later, the following day, when I now changed to chi-square, they say, they are hearing something familiar now. Because even though they don't know much about it, but that chi-square is common people say chi-square. So that's why I usually start with chi-square before we move it. For you to first of all wet the ground, for people to understand the concept. T-test is very simple to explain the concept first before. If you look at it now, sample mean, target value of population mean, sample standard deviation, and number of sample, which is sample size. Now, what are the assumptions? Okay, before now, well, let me just. There are some. Okay, this slide. Maybe let me go and show this slide first. So, having said that, I want us to first look at different type of tests we use. Different type of tests carry out. Hypothesis test. So now, this table tabulates the different type. There are a lot of information. The first column that is that blue is harboring two information, pieces of information. The other one, the other two row column are actually harboring only one type of information. Now, there are some tests. Yesterday we demonstrated number distribution. It's a theoretical distribution. When they say theoretical, it has been proven over and over and over in medicine, in engineering, in pharma, any field to be true. So that thing I told you that in between 68, middle 68%, in between middle 1 standard deviation minus 1 to plus 1 standard deviation, 68.2 something percent of people lie in between. Sometimes we approximate to 68%. 68% capture from the value that correspond with minus 1 standard deviation to plus 1 standard deviation. Whether you are dealing with engineering, anything, you are measuring distance, the rod, length of rod, you are measuring weight, height of anything, in blood sugar, age. Think of anything you are measuring it. It gives you anything that follow normal distribution. It's like that. It has been proven over and over. So anything that has been proven, it becomes a law. So, and they already make it easy by the intelligent people creating that standard normal distribution where you convert each value to standard deviation and make it universal. So we'll be talking of standard deviation. We won't talk about kilometer if you are talking of a road. You don't talk about gram, weight or height or blood sugar. You have already converted it to a disease score. So it's universal. That's why it's 1 gram. Standard normal curve is 1 gram. So it's a theoretical decision that will be proven. So if when you want to do your analysis, you can assume that this variable you want to analyze follow that pattern. So the appropriate test you use is what we call parametric test. The hypothesis test you use, they are classified as parametric. Some of them you can see in that column: student t-test, peer t-test, analysis of variance and over, 1 way and over, 2 way, whatever, Bayesian correlation, linear regression. These are they are parametric tests in the sense that for you to use them, you have assumed that this variable, whether weight, height, or whatever, follow normal distribution. Naturally, a variable may follow normal distribution, but in your own data set, they don't follow because of the presence of some outliers, either negative or positive outlier. So you remember I told you yesterday when we were talking about that outlier, when we were talking about that no outlier would make it. So in that situation, there are things you do. So if you cannot say that this thing follow normal distribution, you use non-parametric counterpart. Because parametric means from population parameter. That is something that is already that behave in the population in a way. So when you say something, the weight vary in the population, follow normal distribution. Population, not sample. Population, that parametric. Anything parameter is population. You have already said it. So when you say parametric test, if you believe that that thing follow a theoretical distribution, but the one you cannot assume that this thing follow a theoretical, call it non. You see, chi-square test, feature is that test, test for trend, for maximum chi-square, all these forms of chi-square, they are all non-parametric because, of course, you know that whatever you use is categorical variable you use it for, they cannot even follow normal distribution. That's why it's like that. Then when you now come to student t-test, If by the time, you want to use it for something, you say, assume follow normal distribution, and you now do what we are going to do today, trying to see you exploit what we explored yesterday now. For we did normative test, choreograph, and Shakiro test that we did, and all this histogram will show to see that something is not normally distributed. When you do it, you'll be able to wait. This thing cannot use parametric test, even though it's a weight. It's a blood sugar that's supposed to, because of something. You can use some non-parametric counterpart of student test, like we see Wilkinson ransom test, man with new test, Kendall's test. Then for PAT test, you should Wilkinson sign test. Can you see? Wilkinson ransom test different from Wilkinson sign. We run all of them. That's why I told you this thing is over 3 weeks. Analysis of variance, and over 1 way or 2 way or whatever many way. The meaning of 1 way is that if you analysis of variance is what you use. Okay, I've not even started explaining. Okay, the non-parametric counterpart are this: Pearson correlation, kind of correlation, and the non-parametric counterpart. Then linear regression, logistic regression. Now, I just ran through the last 2 columns, which I say is only one information, just to know if it's parameter or not parameter. But what determines which one you even use? What even tell you that you are going to use student test ab initio, that you now, when you do your test of normative, and say, oh, it can be Wilkinson. What even determine that? So that is the purpose when you say purpose. So when I say 2 information are loaded there, one is the study design. That is whether you are dealing with 1 group or 2 group, even if it is 2 group of data. When you say in statistics and research, group does not mean physical group alone. Yes, it may be physical group. There is actually the group of data. It's actually the group of data. Of course, if you collect data from 2 physical different groups, it's independent. But if you collect data from the same group on different occasions, we call it dependent or paired, because it's the same group before and after. So if you measure somebody's blood pressure sitting, and you measure another person sitting higher than this other person, when you measure them standing, if it changes also, that one that is standing will still be far higher than this other one, because whatever is reading standing is affected by the one is sitting, because it's the same person. And you see now, that's why it's called dependent or pair. But pair is a misnomer. People say when you say pair, they will be thinking that there are 2 groups. No. Pair, what you pair is the data collection, the data set you collected. So somebody, when you take blood pressure sitting and standing now, you have 2 data collection set, the one sitting and standing. But you pair it on 1 person, that each person had 2 reading. And you see now, that's what they call it, pair group. Now, so when you want to sample size, then you want to know the type of variable. So it's not sample size, the study design, that is, are you dealing in 1 group or 2 group? Then the type of variable. Are you dealing with categorical or numerical? Even ordinal, all those things you want to know. So those are things that determine the type of test you do. For example, number 1, the first row, compare proportion between independent groups. Then you don't only know proportion. Proportion means percentage, or it can be expressed in decimal. So what do we summarize with proportion? Is what is a categorical variable? You don't carry like sex, the religion, like ethnicity. It's percentage. Oh, what percentage is Hausa, Igbo, Yoruba? You tabulate that. Everything add up to 100%. But when it comes to age, now you're talking of mean age. So now, when you are comparing proportion, you know that you are dealing with categorical variable. Between independent groups, that is, these groups can be 2 separate groups, or 3 or 4, or even many. That's what you see. Between independent groups, they are independent, and they say that they are separate groups. It's just like maybe you say you want to do the blood pressure, compare. You have for 100 level, 200 level, 300 level, 400 level, 500 level. You're comparing the proportion that have hypertension or that have elevated blood pressure. elevated blood pressure. In that situation, that proportion compare across, it can be across through group of as many groups. Yeah, of course, by the time too many groups, we usually collapse because it makes the sacrifice when we have too many groups. Now, if you look at it now, you will use chi-square. Chi-square. You know, Fisher exact you see is when there's a by the time we get to chi-square, you got to know the condition where chi-square is not valid. Yes, you are supposed to use chi-square, you use it, you not discover that this thing is not, you calculate Fisher exact. The computer will bring it out anyway for you. So you now use Fisher exact instead of chi-square. Then we have chi-square for trend, Then compare and observe frequency with a theoretical one, measure of goodness of it. You know the way we say that you have one group for you calculate the mean blood pressure, you are comparing with the average in the school. It's the same thing. For example, if they do the blood group of 9 university students, and you do their blood, you now say, what proportion out of about 400 you selected, what percentage is A, what percentage is B, what percentage is AB, what percentage is O. We are talking of the ABO. We are not considering the resource factor. You know, there are two blood group systems, the ABO and resource factor, which are covered. We are talking of ABO alone. So in that situation, you have 4 groups. And you have seen the percentage. But maybe in the clinic, Dr. Gazama has already done, when the student come for the clinic, already done their blood group for, and there's this percentage they have that so percent of our students actually A, so percent B, A, B. So you now want to compare from the sample you take. You see the same thing. Does C is it actually taken from that university? That is, does it reflect university? You want to see, does it fit that percentage fit into the one they have known before? That's measure of goodness of it. Now, the one when you do it, you may see, you're going to see the variation in the percentage, but it may not be much until you put it to test to see. Just those are the slight variation is due to chance. It may be due to chance. That's why you do the test statistic to see if this observed difference you are seeing from between this percentage is nothing. It's due to chance. You will know from the chi-square of goodness of fit. So you use it to compare observed frequency with a theoretical one. So in here now, you are not comparing 2 groups. It's not 2 groups per se. So they will not even the one they have in their clinic, they will not give you the sample size. They will only tell you that for each of the 4 groups, these are the percentage we have. You're like the other one, we say you do the mean, and they already know you collect, you measure their blood pressure, and the mean is already known. It's the same thing. It's only that one is for quantitative, but this one is categorical. In this situation now, you just compare, it's one group you have. You're just comparing the frequency with the theoretical one, the one that have been known as measure of goodness of fit. So we still have chi-square for trend. That one we do it in a situation where you want to know when your exposure variable is ordinal. For example, now you want to know the way the student, what do I say? Maybe employment status. This is what we're going to use. Employment status of people. So you now have their social, you constabulate employment status with level of education. So the outcome variable is level of education. The exposure variable is the the outcome variable is the employment status, either employed or not employed. The exposure variable is level of education. Because that, yes, outcome variable must be dichotomous, that is either yes or no, that 2 groups, employed, not employed, followed by normal distribution. But when the exposure is ordinal, because education is ordinal, no education, primary, secondary, tertiary, is ordinal. We know that all animals are equal. Some are more equal than the other. As you are somebody, primary is higher than no education. Secondary is higher than primary. Tertiary is higher than, you know that. So you want to see how does the employment status vary with that level. We use chi-square test for trend. And most of the time when we go analysis, means the examiner don't do for it. When even put it and they are confused, they end up feeling the person what they're doing is money. It's only few people that maybe know little statistics and not say, yeah, you should have done cash care for 10. So sometimes I analyze the paper, I just go there and I see maybe it costs more headache than something. I just leave it. So if they not demand for it, you can run it. It's there. How to run it will show you. Now, compare proportion between pair observation. Can you see? It's still proportional, categorical. But here, pair observation, for example, now, the example we are going to use now, imagine you have an intervention that reduce BP, blood pressure, and you now, first of all, do your baseline, where you measure the blood pressure of the people in the community. Of course, now, it's not just blood pressure you're looking, you categorize if they are hypertensive or not. So okay, this when you first of all you say hypertensive, non-hypertensive, you know the proportion that are eventually hypertensive. You now do your work, you now do your intervention, you prescribe exercise, prescribe different things, drug, and then you give the health education, everything. After a while in the community, you go again to measure their blood pressure. Of the same people, this is when we say peer observation. It's not as if maybe that's the mistake many people do. If they are doing community study, they just go to say want to do intervention. When they go there, they take their data and now come back and take data in the same, but not from the same people. So it's going to cause you problem it depends on that type of analysis you want to do. So it's more like independent group. Because it's not though some of them may still be there, but some you cannot say exactly is all these 400 I'm taking now, all the 400 I took before. No. But in peer, you must write their name down. You must know them, address, everything. And when you are and the recording you have for each of them. So when you come back, each of them, when you are analyzing, entering your data, you must enter in the same. If number one is unique, in post after number one must be unique data. You put there in that number one. So that of course now, since it's categorical, you are not it's not only the blood pressure. You want to know are they hypertensive or not. In that situation, you will know the proportion that are hypertensive before. After you do it again, what proportion are hypertensive? If you look at it, it's the same people before and after. And you are looking at proportion, you are not looking at mean. So that's why we use NEMA chi-square. So you see anything that has to do with chi-square now, they are non-parametric because it's dealing with categorical variable. Now, let's now move to the one that are mean. Compare means of two independent groups. Now, this one now, you have two groups. You maybe measure their hemoglobin concentration, or urban or rural group people. You take the blood of a student, of a children under 5 to know if they are anemic. Then you measure. Here now you are not comparing whether anemic or not, because if you want to compare whether anemic or not, you have to have a cutoff, and in that one you use chi-square. But here, before you do that, you want to first of all compare the mean hemoglobin concentration or PCB. In that situation, these two groups you use student t-test if it follows normal distribution. But if you cannot demonstrate that it follows normal distribution, you may use. I will still come back to all those assumptions. You may use what we call all these other, any of them, but most of the time matter with NIU, because that is the counterpart for two independent groups. If you can, that's a non-parametric counterpart. Those are non-parametric counterpart of student t-test. Now, test of mean of different in peer observation. In this case, now there are not two group people, but it's mean you are comparing before and after. Just like what I say, you take blood pressure sitting and standing. You are comparing them. That is before and after. You use peer t-test. You know, all these t-tests are the formula I showed you before that I used to explain, but they're actually simpler. They are used to explain to bring out the logic behind hypothesis test. So the non-parametric counterpart, if it doesn't follow normal distribution, after you have done your abracadabra to test if it's normally distributed, you cannot substantiate. You can use Wilkinson sign test. You can see the difference. The other one is Wilkinson ransom test. This one is Wilkinson than sign rank test. You get to know.
You know the lazy day for me. That's why I just did everything low.
You are,
Like,
you are disturbing the class. Please mute. So now, if you are dealing with test or mean of different, okay, compare means of more than two independent groups. Okay, this one, you see how mean comparison is different from proportion. Proportion, when you are dealing with independent group, whether 2, 3, 4 is the same cash flow. Then when you come to the comparing of mean, there is one for two independent groups, there is one for more than two independent groups. If you are having 3, 4, or 5, that is analysis of failure. We follow normally. And why is it that when we get there, you know the reason. You cannot use T-test to compare group of more than one between group that are more than 2. And the non-parametric counterpart is Kuka-Wallis one-way ANOVA. When we talk about one-way ANOVA, what it means that, for example, you have two groups. Imagine you have a group, you are doing exercise, you have an exercise training center, and you are trying to measure weight of you have people maybe you prescribe exercise. So it's not only exercise. The weight loss program. You prescribe exercise for one group. You prescribe diet. You want to know the difference. You now have one group that is controlled. You didn't even prescribe anything. So you have 3 groups now. If you just look at you measure their weight. If you compare the mean weight of the 3 groups, that's one-way ANOVA. But if you want, because the weight is the factor. I've already told you the what do I call it? The exposure variable. We call them factor, risk factor, determiner, predictor. You can call it different name like that. So in this one, the group, the factor here now is the type of prescription you give. Is the person, is it exercise? Is he weight loss? Is it diet? Then we have control. But if we now introduce, you also want to know the difference between male and female. That sex you give to it can produce another. That sex is another factor. Apart from the group 1, 2, 3, exercise, diet, and control, you also say between male and female. That's another factor. That is two-way ANOVA. If you bring another factor, you want to see black and white into it. That is another factor. That is 3-way ANOVA. Whenever you have more than one way, once you have 2 factors, we call it factorial ANOVA. It's not a big deal. Just name factorial ANOVA. You ever heard of factorial ANOVA? One time where you have a part where some people just say factorial. They say, no, because he's doing master in but statistics on that one is not for you. I just look at it. And at the end, they don't even know anything about it still. They just know some rudimentary what is there. So there's no big deal there. So now, Kuka-Wallis, one-way ANOVA, Feldman, two-way ANOVA, those are the non-parametric. And then determine the degree of association between 2 quantitative variables. If you look at the one we have done before, you have group. Because the chi-square, we say comparing proportion between independent groups, is another way of saying association between 2 categorical variables. Association is chi-square. Because the proportion, is categorical. The 2 group or 3 group itself is categorical. Group does not have number, it's not quantitative, it's a factor. The group we belong to is a factor, is a categorical. So you are looking at the group through the proportion, the percentage. So percentage itself is proportion itself is categorical. The group itself is categorical. So you are looking, so the 2 variables you are looking at, both exposure and outcome, they are categorical. That's why is association between 2 categorical variables. That is chi-square. But when you come to T, you will see that you are comparing mean quantitative between groups. So the outcome in chi-square, the outcome is the exposure is categorical, the outcome is categorical. But in T-test and ANOVA, the exposure is categorical, the outcome is quantitative, because you are looking at the mean between 2 groups. Because the outcome is the what you want to do, maybe blood pressure, hemoglobin concentration. So the exposure is whether they are urban or rural. the group they belong to. So in this situation now, if when you are dealing with a still test and ANOVA, you are looking at association between categorical exposure and quantitative outcome. Does it make sense? Now, there are some situations when intelligent people came with the idea, okay, we can actually look at association between quantitative and quantitative. Both what you think is due to and what is leading to, both of them, they are quantitative, they are numbers. So you use correlation. If that thing color normal distribution, especially if it is continuous variable, it's Pearson's correlation. The one thing about Pearson correlation generally is actually there is nothing like exposure and outcome in correlation. Both of them, the two quantitative variables you are looking at together, anyone, there's no, you just also know how do they go together. As one increase or decrease, you are going to do it. So there's no correlation, there's nothing like exposure or outcome, no dependent, independent. But you know that association, degree of association is a degree because it varies. That is degree of association between categorical. When we cannot sure, we are not sure, especially now, if you are dealing with a continuous variable, Pearson correlation. If we now introduce one rank variable, for example, now education, you know, it's ordinal. You can rank it. No, formal 1, primary 2, secondary 3, tertiary 4. You rank it. It's number. You know that's the non-valid rank. Because of that, the intelligent people spend money. So in this situation, they now create another test called Spearman rank correlation or Kendall. And Kendall is preferred to Spearman in a situation where we have a lot of tie rank. Tie rank means that when you have too many ranks that are the same. Imagine when you give your questionnaire for all these like SK, they agree, disagree, not disagree. Some people just put somebody disagree. They just be writing, you know, when you didn't collect data very well. They just write one convenience. You now see that almost all of them talk about strongly disagree, or strongly agree, strongly agree, strongly agree. So in that situation, you have too many tyrants. So Kendall, and when the sample size is also small, so Kendall will be better. Apart from that, if once you have a rank, Spearman rank correlation. Now, this is second to the last one. Determine the relationship between a quantitative dependent variable. Can you see? That is the outcome variable. And other variables. That is, you are trying to look at the relationship. This variable, the outcome variable must be quantitative. Most of the time, must be even continuous. The other variable, the exposure. It can be one exposure variable or many exposure variables. If it is one, if it is, and the exposure can be quantitative, it can be categorical. So in regression, linear regression, is the outcome that needs to be continuous. The exposure, either one or many, can be anything. So when it is only one exposure, we call it simple linear regression. But when we have more than one exposure, we call it multiple linear regression. So now, the last one, determine the relationship between categorical dependent variable and other variable. That is, the outcome is categorical, maybe yes or no, or die or maybe outcome, disease or disease, or cure or not cure, no, treated or not treated. All those outcomes that, though you can have outcomes that are more than 2, but whichever way the outcome is categorical, we call it logistic regression. You know that the exposure can be linear, can be quantitative, can be categorical, can be anything, but it's the outcome that's categorical. Can you see the difference between the linear regression? And it's the same thing with logistic regression, because in logistic regression also, if the exposure variable is 1, it's simple logistic. If the exposure variable more than 1, 2 and above, is multiple. So is this multiple logistic regression they call multivariable analysis? It's not multivariate. So many people make that mistake, they say multivariate analysis. Multivariate analysis is different thing. So in multivariate analysis, the exposure, if you look at the linear regression and logistic regression, which is multivariate analysis, the exposure is only one variable, but the outcome is only one variable, but the exposure can be one or more. But in multivariate analysis, even the outcome can be many outcomes. You are trying to get together. For example, now you want to, instead of you saying, many times when you are studying blood pressure, blood pressure is systolic and diastolic. So many people, they don't regret the blood pressure, systolic and diastolic. They rather change it to hypertensive or non hypertensive and now use logistic regression. But if you want to run it like linear something, the way the value are, make sure that you are having two outcomes. You are having systolic blood pressure, they are separate, diastolic blood pressure. So in that situation, and you have many exposures, so that is what we call multivariate analysis. Example is multivariate analysis of variance. We have multidimensional scaling, factor analysis. Those are the example of multivariate analysis. But linear regression, multiple linear regression, and multiple logistic regression, they are multivariable analysis. The variable they are talking about is that they are looking at many exposure, multivariable analysis. Now, you will see that by nature, linear regression is parametric, logistic regression is non-parametric. Now, how do you take decision about whether to use parametric or non-parametric? There are some assumptions about parametric tests. Now, you see, we talk about normal distribution. Normal distribution is just one and the most important factor. But there are other three factors that also to follow in that parametric test. But the most important one is normal distribution, normally distributed data. They are arranged according to importance. The number one is the most important, followed by number two, followed by number three. Number four is the least important. Normally distributed data, that is, it must follow normal distribution. And you can do that by doing what we want to do. We want to do transformation, we do that. In the practical session, we'll do that. How do we do something? Test. And we do, I don't have yesterday to test for normality. We have done that, but we'll do something else. Homogeneity of variance. Homogeneity means homogeneous means the same. Doesn't mean. So when you have either you are dealing with two groups, which is t-test, or you are dealing with, that when you say assumption, maybe you will talk about telling me because Kafka has nothing to do with parametric test. We're talking of those one, t-test and over. Now, homogeneity of variance means that if you have two groups or three groups, even though, of course, the mean are different, that's why you are trying to test if the difference is statistically. But for you to be able to use this parametric test, the variance must not be significantly different. Even though the mean are different, the variance, the variance is measure of variability around the mean, must not be different. Not that it will not be different in figure, but very close. By the time you put it to test, you say that, no, there's homogeneity and variance. But if it differs, there's heterogeneity of variance. So normally distributed data, number one. Number two, homogeneity of variance. Three, data should be measured at least at interval. What does that mean? At least at interval. I want to know. Somebody do this workshop, somebody do unmute and tell me. What do you mean by it must be measured at least at interval level? I usually ask this question. It's only few people that usually get it. What do you mean by that? Nobody. Nobody. What do you know? Okay. Now, if you remember the scale of measurement we talk about, we talk of nominal, ordinal, interval, and ratio. Because we are rushing, there's something also I didn't when we were discussing that scale of measurement. You will see that nominal and ordinal, we even said it also, is for categorical variable, while we have interval and ratio for quantitative variable. So it means that it must be a quantitative variable. So it must be measured at interval level. But then it's this one can be violated. You know, it's not as important as the first two. Because sometimes when you do your test, all this perception, attitude, you score 1 to 5, 1 to 5, 1 to 5. And you know it's ordinal, it's not interval. Because it's just the strongly agree and disagree, it's not, they are not value. But because they are hierarchy, that's why for convenience we rank it 1, 2, 3, 4, 5. So if you now try to compare the two groups now, you are going the mean score of each of the questions compared between two groups. It's being done. It can be done especially if the sample size is very high. Because you get to know later that not all this assumption will be met before you can use parametric test also. I will tell you this. So sometimes it can be violated because it's not as important as the first two. So in a situation where you use all those like SK and you score it and you now compare with students, you can do that, especially if the sample size is very large. Then independent. What's the meaning of independent? If I ask you this one, who knows it? Meaning of independence, yeah? You know, if you remember, the when we are comparing between two group and one, we say two group, independent group, peer group. So when there's peer group, I've told you it's peer or dependent group. So when we say independent, that is two, it can be two or three separate groups. The dependent means is the same group of people, but you collect your data on two occasions. The data must be independent. That is, it must not be from the same group. But if you look at impaired t-test, it is violated because it's the least important. Can you see? It's the least important. That's why it's violated, because in the paired t-test is dependent, and the paired t-test is still a parameter. So how you check for normality? I think we have done that yesterday when we talk about percentile, quarter. So, and then how you quantify UC, Komogorov-Smirnov, and Shaplov-Wick. Discuss them. And then what are the approaches to problem of non-normality? In a situation where you expect this thing to follow normal distribution, and when you do your test now, test of normality, it doesn't follow. What will you do? There are 3 things recommended. But the first one is the most important. That's the first option you consider. If you cannot consider the first option, you use the second option. You cannot do the last option is the one you should even avoid. Now, the first one rely on the robustness of the test and still carry out parametric test. A robust test is a test that is still valid when not all the conditions for using a parametric test are. No, we already told you, if you already gotten normal distribution and homogeneity of variance, if the independence done there and this at least interval is not there, even sometimes, even if it's normal if the sample size is very high, so you can use the robust test. So t-test and over their robust test. Then you can use a non-parametric test. No, we have already shown you the non-parametric counterpart for each of the parametric tests. You can decide to use man-Whitney use instead of independent t-test. You can use Wilkinson time rank test instead of using air t-test. Now, the last option, which is not encouraged, is transform the data into a new set of data that are consistent with the assumption and carry out the parametric test on the new data. So we are going to, one of the major problems, I'm going to show you how to transform data. And we will do it with SPSS. Now, one of the major issues here is that when you transform data, the life is never the same. So, for example, now, if you do mean, and you transfer it to logarithm, the mean of that logarithm is geometric mean. You know, the mean of logarithm is geometric. It's not arithmetic mean, because logarithm is geometric analysis. So now, if you now, after you calculate the mean, geometric mean, you now calculate, you can reverse to calculate anti-logarithm for that mean. It will be equal to the median of the original arithmetic median, not the mean of the original. And you see where it lands you now. So that's why it's something that you don't actually contemplate. It's the last option that should not be even contemplated when it comes to look at approaching the problem of non-normative. So now, when we want to transform the type of transformation, the type of problem, situation, if something, we have already said that what makes that not to be normally distributed, whether it's skewed, positive skew or negative skew, or unequal variance, heterogeneity of variance we just discussed now. So if it's positively skewed, you use log normal transformation, more skewed than log normal. The situation. If the skewness is you lose logarithm, reciprocal, and square. I will demonstrate some of them now. You will see it's on the next slide. Negative skewness, you use square. Can you see now? Positive skewness, you use log. Reciprocal. Reciprocal is 1 over that thing. You know that when you do 1 over that thing, the largest becomes smallest. Then square root. Square root is used for positive skewness. Then, but if it's negative skewness, you use power transformation. You use to power 2 or 3. Unequal variance, you use logarithm, reciprocal. So that's the way you treat positive skewness. Positive skewed is the way you treat unequal variance. Now, okay, let me look at an example. This is an example of square, cubic, and square root transformation. You see, if you list a number x, list numbers here rather 1 to 10, you will see the difference in each of the subsequent number is 1, 1, 1, 1, 2, 3. They are serial 1, 1, 1. The difference between each of them. Then when you square, what happens? 1 becomes 1, 2 becomes 4, 3 becomes 9, 4 becomes 16, 5 becomes 25, 6 becomes 36, 7 becomes 49, 8 becomes 64, 9 becomes 81, 10 becomes 100. Look at the distance between them. 1 and 4 is 3. Then 4 and 9 is 5. You use 9 and 16 is 7. You use 16 and 25 is 9. You use 25 to 36 and 36 is 11. You use 49 to 36 to 49 is 13. You use 49 to 64 is 15. Between 64 and 81 is 19. This other one is, can you see, 21. Between 81, okay, 19. The other one is 17. 19. Can you see? As the value increases, the gap in their difference begin to skyrocket. Look at that's square root in square. If you see cube, that one is worse. Can you see? It's more. Now, look at square root. You see 1, 1.4, 1.72, 2.2, 2.5, 2.7, 2.32. So you will see that for power transformation, that is square and cubic, you see is widening the distance between each value. But for square root transformation, it collapses, it reduces. Look at between 1 and 2 is 1 before bed. 1 and 1.1 is not equal to 1. Between 1.4 and 1 and 1.4 is not equal to 1. The difference is not to 1. Between 1.4 and 1.7 is not to 1. Between 1.7 and 2 is not 1. Between 2 and 2.2. So you can see that the distance is collapsing, shrinking. So now, if you have a negative skewness where you have some extremely small value, which is is extreme small outlier, you want to jack them up. That's why you use power. Look at a power transformation, square and cube, because you are dealing with negative, because there are some outlier that are so small, you want to jack them up so that you can widen you make them up. But if you have what do you call it, positive skewness, you want to shrink because there are some outliers that are too big. You use square root and logarithm. Can you see? Or reciprocal. That's the logic behind transformation. And this is a form of logarithm transformation. So you will see this thing. You will see that we have at the upper part we have log, and the lower part or normal x. The other one log x. You will see from 0 to 1 to 2. You will see from normal 1 to from 2 to 3 under log, you will see that the difference in the normal something is 900 between 100 and 1,900 different in the normal scale. That's between log 2 and 3. Between log 1 and 2, the difference is 90. Can you see? 100 minus 10. Between log 0 and 1, the difference is 9. Can you see? Then between minus 1, you know, the log that is 1, 1, 1 you are seeing. The minus 1, the negative, you now see the difference is 0.9 from 0.1 to 1. So what logarithmic transformation does is to, for smaller values, it widens the space between them. That is, it jack them up. That is, it jack up all the smaller values, give them more value. The bigger value, it bring them down. It's just like if you want to, what some people want politically, what is politically popular to masses is that they should collect all the money from the rich people and distribute it equally. But they don't know that if when you even do that still, it's a matter of time. The poor will still be poor, the rich will be so rich. But what the log transformation does? You collect and shrink, bring down big number and jack up small number. So in that sense now, somehow, it has a way of even correcting both negative skewness and positive, but it's more for positive skewness. That's logic. We have done this one. So any question? Any question? So that we go to our. Somebody, any question? No question? Okay. Well understood. Some people don't want to talk. Okay. Who will share the same skin lesion? Who will share the, so we want to do logarithm transformation. Want to do transformation now. How to do the transformation, logarithm transformation, the most popular transformation people do. How to do it with the SPSS. Who will share that same? That's great. That's Mukhtar. Great. So go and look for your skin lesion and bring them out. Bring it out.
I can share.
Yes. Then somebody is already, you are looking for where you see. If you have not changed it from, is it still in Excel? You have not read it at SPSS, Mukhtar. Mukhtar, talk. Farouk. It's not Farouk. Mukhtar. Unmute and talk. Unmute.
Yes, sir.
If that's it, so you click on that file type, you see that by default, SPSS statistic, there's an arrow in front. Click it and go and click on Excel. So because it's SPSS by default, that's why it's only the SSS file is seen. You will not see the Excel, but click on that arrow down. You will see Excel option. So remember the Dr. Dimas did it the first day. You didn't get what I said?
I get it. I should click on
this arrow now in front of, no, down, where you have files of type that they put SPSS statistic, they put save, and click on that arrow in the front.
Okay.
Yeah. You know this, you think you know your Excel, click on Excel. Until you do it, if you don't put your hand to do, look at the Excel now, click on it and open, and come and open. So if you don't, you think you know, it's when you open, you can know that, there's even the SPSS module I didn't share, I will share with you today. The SPSS, how to use the module, I have a module for it. I will share. Okay, share. Share again because he's always doing like that. Share again.
Okay.
But if I just do it, I don't allow somebody to do it. So people will not know that they can do it. Thank you. So if you like, you can save now. You can save because it's not tight. You can save as skin lesion. So next time when you do it, you bring the SPSS out. Go to save.
Okay.
File. Go to file. So this is slow. The RAM is small, I think. Or do you open too many applications?
Maybe. Where should I save
No,
it
where
from?
do you go to now? No, it's not. I didn't say save now. You want to click on save file. You want to click on save, clear this thing. Okay, save.
Okay.
It's okay. Yeah, it's okay. So no, go back. Sorry. I think it's the same thing. Go back. I didn't know.
To where? To file?
Yes, file. Oh, that's the file. I mean, okay. But okay, you want to save directly.
Yes.
I thought when you put file, I will see save as. Okay, just do it. Okay, now type in the file name, type skin lesion. Type skin lesion. Where is it not even? Where is it not? I don't know where you went to because it's open. Is because it's supposed to give you safe. You are still going to open. Close. It's file.
Okay.
If you click on file, don't go and click on save. Click on file first. You want to save. Is it under file? Is it save under edit? I don't think so. Okay, type it and put on that and press your this thing.
Press what? Open?
Please. Yes, open here. Just click English. So type of okay, you know what? Global, don't put gap in the name. Let's see. That's not the issue. But you can actually put gap in the name. You have not gone to save for you are not gone. That's why it's giving you. Okay, maybe you should, I don't know. Log out, let another person share, please. So that we don't delay. Who will share?
Let me share.
Okay. Stop sharing, let another person share. See the way the person is doing. Yes. Yeah.
Sir.
Okay, you have not. Okay, now. You have not because you are reading. Yeah, click OK. Where you are now. We are on the way to read it as click OK. Thanks, why. So you can see it's okay. Now, go to, if you want to save it, go to file. How do you save? It's not file. He was clicking on the something below. Save as. You now put skin lesion there in that place that is say on title. You can even add that, it doesn't matter. And skin lesion.
Let's change the phone.
It may no, you can write it anyhow you want to write. Skin lesion.
Okay.
Save. So Mukhtar, can you see now? So it has helped you. If you go back to that place, it has helped you save it as you have both the Excel and the SPSS. So you don't need to be looking for it. It's an SPSS. So now you remember it's the age we explored yesterday that we see that it does not follow normal distribution. So go to analyze. Go to descriptive statistics. Explore. No, you are not there. No, my hand can be explore. That third option. Explore. So put age there. Move that age inside.
That's here.
Yes, now you know it's serial number you have, it's not age, return it. It's serial number. Age, click on that age. No, click on that arrow. Yes. So click on plot. Plot. Click on histogram. By default, because stem and leaf give more information than histogram. So by default, they put, even if you don't even put it, run stem and leaf for you. But I've already told you because they are doing the same thing, but stem and leaf give more information. Yeah, click on the histogram. Then click on normal plot with tests. Those are the Kolmogorov-Svinov tests. So continue.
Sorry, stem and leaf is still there.
What is it? Yeah, it's okay like that. Continue. Okay. Great. I like your computer. So it just shows the something. Why didn't the something view now up there? Is it that one? It's not that one. It's not that. It's the one up now. Yes. So you can see what we did. Scroll down. Just scroll down. All those things I just want you to see what we did yesterday. Scroll down. Okay. Scrolling down. Let people see the test of normality, so that is not normally distributed. Yes, we need to go down, scroll down. You see the histogram, you see the shape. See, you see, yeah, we're scrolling down. I don't want you to see that the same thing we did yesterday. Same and leave. Then scroll down. Scroll to the last one. You see, in your own data set now, the way I arrange, the way when you have manipulated something in your computer, the position of all those outliers is not the same place, not the same number in our computer, because sometimes we sort all those stuff. It doesn't really matter. You can see that it's not normally this because the median line is not in the middle. So we want to transform now. So you have to go to data editor window. You want to go now. You go to data editor. Let's see. Data editor window. You can hover on the SPSS on the taskbar. SPSS icon on the taskbar down. Over, put your cursor on it. Put your cursor on the SPSS taskbar on the ground, on the lower part of this pane. On the right corner, the icon of SPSS.
Icon of SPSS.
No,
okay, here.
Over. Yes, over on it. No, the SPSS down now on the pane. Over, just put your cursor on it. Yeah, can you see now? It will show you because you are in a result view. Click on the other one, screen reach on the data editor window.
Okay.
Click on it. Yeah, thank you. So another way of doing it, if you go to window, it will show you the two. You click your cursor on the window up. You can. So that's how to move between. So now, though it doesn't really matter self, you can even want to do the transformation. You can even access it from that place self. But it's just for you to come to variable view. Click on variable view. Click on that number 8. That's V8, number 8 on the left side. It's not that one. That number 8 itself on the left. Number 8 is not that one. That number 8, right click. Right click on it. Clear. Click on clear. because that one is an active party there. You can control S to save, so it doesn't appear. Now, the way you do transformation, go to transform. So compute variable. Click on compute variable. So you see that. So click on the variable log age. Just type that target variable log 8 in log age.
Log age.
Age capital A. Age. So you want to do logarithm of age. So come to, you see function group on the left side, on the right side rather. On the right side, use function group. We'll click on arithmetic. Logarithm is arithmetic. Click on arithmetic. Click. As you click, all those ones that are under arithmetic, they come down as function and social, so and special variable. So ln is the natural logarithm we are looking at. ln, click on that ln. ln, natural log. It's not logarithm to base 10, natural logarithm. Click.
ln.
Yes, click on that now. You are there. Just click. Immediately you click, it gives you something here. So it gives you say ln non exponential numeric whatever. So there's an arrow above you. Click on that arrow. There's an arrow. Yes. Immediately you click on it. Click. Can you see now? Don't click again. No. You say ln of what? So go and click on H. You want to use that H to replace that N in that bracket. Just click on the H. Some people, they make mistake, they shift their hand. They go and put it outside outside the bracket, and the thing will not go. Yeah, click on the H.
And this arrow.
No, you don't. Yes. Put it. Arrow. Yes. Can you see? So you say logarithm of H. That's all. So just say okay. So now go back to your this thing. No, you have not. You have just done it. You have not run it now. Go back to your data editor window. Let's see. You will see. Go to your data view. Even the variable view, can you see log H is there?
Yes.
So can you see two decimal places in the, go to data view now, data view. Click on data view.
I've clicked on it.
So you will see can you see it has done all the logarithm of H here, the last column. That's logarithm. So if you want to know if there's an improvement because it has transformed, it has done logarithm transformation of H. Let's see if that formation improve on the skewness. So we'll go to analyze. Descriptive, where you went to the descriptive statistics.
Explore.
Then explore, the same thing. Remove H and put log H. Return H and put log H. Click on it now. So put the log H now. Now just say okay, because all those things you have set, they are still valid. Just say okay. So can you see? You can give me be scrolling down now. The main, if you look at the number, is smaller than the other one. So let's look at the homomorphism. If you look at it, both of them were less than 0.01, but the homomorphism did not change much. But Shapiro-Wilk changed because it was less than 0.01. So 0.01, it has become 0. Though it's still skewed, though. That's so that pattern was extremely skewed. So it's still skewed, but the skewness, the p-value has really increased. You know that the more the p-value increase, the more is more likely to, but it's still significant because the p-value is less than 0.05. Okay, look at the graph. Yeah, scroll down to look at the graph. Can you see? If you look at it, it's better than the other one in terms of the skewness. Go to the other one. Go to the other one. That percentile. Are you seeing? It's a little bit better. Then go to the last one, which is whisker. If you look at it, though it's still, the thing is not perfectly in the middle, but the thing is close to the middle. The median line is closer to the middle line, the other one. So that's how to do transformation. This is how to do logarithm transformation. Are we together? Any question?
Yes,
Any question? So I want people to go and do all these things we have done, because from tomorrow now we are no more using this screen lecture. Then I will send, I forgot the what I call it, this and the module. I will send it to you. The module for the expresses, and I actually even use in that module. I explain even using this screen lecture to do a lot of it, because that's why I actually need to start. But tomorrow now we start analyzing with normally we are supposed to start the chi-square today, but 12 minutes to now. If we now start chi-square now, I have to talk about theoretical concept before we analyze. So no go away. I'm sure people are already saturated. So I think we close here. Any question? Because all those other one, I don't want to run anything that we have not talked about. It really like magic. All this one we have done. Try and go and do them. Yes?
Yes, I have a question.
Okay.
So if we can use non-parametric tests on this data that is not normally distributed, why do we need to transform? What is so important about transforming data to become normally distributed?
It's just academic purpose. I've already told you. That is better you even go away from it, you don't even do it. So if you look at the option, it's the last option, and it's the one you say you should not even try. So the first option used robust test. The second option used non-parametric counterpart. This one is the last option if you go above. So it's just for you to know, because sometimes they may say, somebody may say, help me transform. That is some people, there are some work you may want to, they are talking of geometric or whatever. So they may say transform. So you should know how to transform. That's all. Even all these other transformation you can do, okay, maybe what's the name? Messi. Click on transform again. Let's do all those all the square transformation, square root, they are out there. Let's do square transformation. Click on transform and compute. Click on compute variable. So type in that place h square instead of log h square. Not to square h.
Is there
H square SQUARE h square.
I should actually write it out.
Yes, right. No gap. Yes, okay. H squared. Then you remove that all those things, the inside, this LNH, remove it. LNH remove. And delete them.
Thanks, Papa.
No, you know, to just remove, delete. You can put that this and backspace. Now, move H there. H times, that's asterisk is times. Asterisk you see in that place, in that keyboard you are seeing. Click on it. Times H again, move H again. Click on the H again. You know, A square means H times H. Okay.
Yes.
Okay. So if you want to, if you check your data editor window, you see the value. If you want to do square root 8 cube, be 8 times 8 times 8. If you want to do square root, I think square root function should be there. It's there also. You go to the arithmetic and give you square root function. That's all. For arithmetic or statistics. Go to your data editor window, you see it now. You see the a square you have done. So you can just do anything in transformation. That's it's just for you to know. Sometimes when you say you know statistics, some people don't understand, they come and cry. If you don't know something, you don't have nothing to fall back on. So now if you now fumble, then the work has left you. The person that gave you work you cannot do, you mess it up. The next one, you now say, I give my work, it didn't. And they now refer me to another person, is the one that now did it very well. So with that person they will refer you to. Can you see now? So if you say you know statistics, you know it very well. It's not the one that is not even your concern. You may, because somebody, even if you have no more, so you can find out, search. The logic between this statistic knowledge is read and do, read and do, practice. That's why when some people are saying you should share, I will tell you what to do now. They are afraid. So if you cannot do simple things, you cannot learn hard things. Because that simple thing come up in 100 times, simple task, 100 times become big. So when it's let me do transformation, as if it's something big. So it's somebody an answer that help me do the logistic transform, log transformation. What is there? Just for you to click how you do it. So that's the essence. So sometimes for academic purpose. Thank you. Good night.
Yes, sir.
Tomorrow, yes, any other question? Any other question?
Yes, sir. Thank you very much, sir.
Yes, sir.
Yes,
So this is about hypothesis, actually.
Okay.
So if you are doing a one-way ANOVA hypothesis testing, like you've already tested the hypothesis, with a follow-up test of post hoc.
We have not
test.
reached ANOVA now. We have not, all this thing is just to give you tomorrow we start with, if you look at the timetable, we are going to run and all this data, the one that are for chi-square, for t-test, ANOVA. When we get there, all these post hoc tests, we'll do them.
Okay.
Okay, thank you.
Okay, sir. But I was hearing something about one-way ANOVA.
I already told you, don't worry, tomorrow we talk, no, it's not tomorrow, the day of ANOVA, we talk much about that. One way ANOVA just means only one factor, that group factor that maybe 3 groups or 4 groups, is ANOVA from 3 group and upward. That one that is 4 group or 3 group, that is the one way. But if you, apart from the group, you now have other factor, and that other factor can be quite dichotomy, can be 2 groups, like sex, like it can be 3, it can be any group. Those are factorial ANOVA. One way ANOVA is just there's only one factor. That group factor is the only one factor. That's one way ANOVA. When factorial ANOVA is when that you have more than one factor, 2, 3, 4. You can say 2-way, 3-way, 4-way. And that's what we call factorial ANOVA. So there's no big deal there when we get there. See. But it's good to even first know the simple thing first. So, okay, thank you. Good night.
Okay, thank you, sir.
Welcome.
Good night.
Hello, thank you very much, sir.
Thank you, sir.
Yeah,
So
welcome.
my question is, I thought after the data transformation, it will be like perfectly symmetrical.
No,
The
if you know,
coordinates
it
should all
depends on
align
the
on the
extent or the damage. If they say somebody come and repair, so but then you repair, it cannot go back to the same as the thing was damaged. That's why I cannot go back to. So it depends. We have done it now, so it cannot go perfectly. It's just to show something. So so that just is, statistic is instrument you use. Statistic will not replace your thinking, your reasoning faculty. You are just using statistic as an instrument to help you. When at the inception, when we talk about the logic of scientific reasoning, I said that the scientist, how does he understand the world? By the senses and reasoning. The senses used to collect data, reasoning through statistics. You just reason. You are just using instrument to help you, just like the way we use computer to help us to do something. So it's the logic behind that we are using. So it's an instrument. It's not actually perfect. That's why you can tell like with statistics. Yeah, we call something biological plausibility. You can do statistics and say it's statistically significant. The people that are in the clinic, maybe doctor that from the experienced patient, they discover and forget what they have seen is different. So it's not biologically plausible. So they will only flag that particular thing if they see that what has been biologically plausible have been supported by statistics. Give them evidence, strong evidence. There was one time a colleague of mine when he was doing a part 2 when I was in Lut. So in family medicine, all these risk factor for hypertension, all this exercise, obesity, everything. Diet. I don't know, but we can see those people that they have that thing. It comes out all those things. I say maybe somebody is cooking data. Those things was a good data set that those people that have been doing exercise before, prolong. They didn't just ask all those rubbish questions. Did you do exercise? No, they look for if you have been doing exercise before. For how long have you been doing exercise? No, they look at. They ask the question very well. They talk about different, even the diet. What diet you have been eating for some time. Not that somebody today now that have gone to the clinic. They say, you are obese, so you have to do exercise. You have to change your diet. And it's just last week, 3 days ago, that he now say, he made the resolution that he had to change his exercise. When you are now asking questions, do you exercise? Say yes. How many times? Every day. Well, that is just yesterday. So that one will not have you. In fact, it's because it's hypertensive, we have the problem. That's why they recommend it. So at the end of the day, when you analyze, you might discover the people that are doing exercise have more hypertension. The people that do have hypertension, they don't bother to do it because they don't have problem. The people that they are already told they have problems, they do exercise. That's what we call the cross-sectional study does not have temporal sequence. That is, you cannot establish that the exposure precedes the outcome. Because some of these people, the person is already hypertensive before he started doing exercise. He was hypertensive before he became obese. So it's not as if maybe is the obesity has reduced, that's why he didn't have hypertension. And you now discover that people that have normal blood pressure, they don't even bother to do exercise. They eat anyhow because they have not been told that you are in danger. The people that have been told they are in danger, they just started now. And you now collect data. It will be rubbish because you now see that, can you imagine the people that do exercise are more hypertensive, the people that do good diet are more hypertensive, they are more diabetic. That's just it. So it's not statistics does not think for you. It's not computer, all this AI they're talking about. Yeah, it's programmed now. It's just to make the work faster, but it will not replace your thinking. That's why if anybody they ask you write article now, you just use what you get from AI. People will know because they have checked. If you use it, there are some things you can use AI to gather some point to which area they want to cover. Because AI, what you just do is to search the web where anybody may mention of those things and now bring it for you. You can ask, okay, these are the points. You can even remove some. You want that are reasonable. It help you gather point within short time instead of you to be thinking. Then you now start writing. You now do your normal literature review around those things. So that's the way to, not that you just say, okay, I write article on this one for me. You now send it for publication. They will just turn it down back to you. They won't ban you from sending anything. So that's just it. So computer is garbage in, garbage out. It's an instrument. It does not replace your thinking, reasoning faculty. Thank you. Good night, everyone.
Good night, sir.
Good night, sir. Thank you.
Good night.
Good night, sir.
Yeah, good night.